We've covered a lot of ground, I'm reminded. So I'm recalled that we started with this kind of cartoon of L-napple and D-napple plumes and what they look like. We started talking about the free phase behavior of these. And indeed, we've talked about the reasons why it stops somewhere, the reasons why it stops on the groundwater table for lighter than water fluids, the form of the saturations that we'd expect to see in here, the rates at which we think fluid would go through these, controlled by relative permeabilities and the residual saturation, the prospects for being able to suck this out if we try to. If it's close to full saturation, perhaps we can. If it's not, then all we'll suck out of here is water. We've talked about rates of dissolution, how it'll carry a plume down gradient, and how we predict the arrival of that plume. We've talked about it both for conservative solutes and for sorbing solutes, non-conservative solutes, and what that ramifications of that are for both the plume as it develops downstream and also for its arrival. It will be retarded in its traveling downstream, and the front will be slightly sharper, and it will be delayed in its arrival at the compliance point. And we know how to figure that out from this value of this retardation coefficient, which is a function of distribution coefficient, which is due to sorption on the solids, which are typically both carbon, majorly if that's present in the aquifer, but also on the grain surfaces. So we've done a pretty decent job of covering that, but we haven't really talked about what happens in the zone between it being spilled on the surface and getting down to the water table or below, or just the water table. And so that's what we'll talk about now. And we'll talk about what happens in the vadose zone and how we characterize these kinds of behaviors, transport what we know about what happens in the groundwater zone into the behavior in the vadose zone. No idea why it's called IMGRESS. It must be the name of the file that I uploaded. So that's our plan for today, to talk about vapor mobility. And that'll, bless you, and that will kind of cap out what we want to talk about transport. The next thing we'll talk about after spring break is modeling of these processes for one session. And then we'll talk about methods of site investigation, which borrows on the stuff and other stuff from Northwest Territories and other things since then. So that's what we're talking about today. I guess I did this scribbling in the past when we were talking about this. So we'll talk about both diffusion, we'll talk about methods by which partitioning occurs and the results of that, and then we'll talk about aqueous advection. So the cartoon that describes all this is this. It's actually stolen from a Canadian. You can tell by the way that vaporization is spelt. It doesn't necessarily be Canadian. I guess it could be Australian or English. And that is that you have a spill. You have free product falling through the vadose zone down to the groundwater zone. And as it goes through here, it'll create a chimney. Some of it will move as free product. Some of it will be smeared on the chimney as residual. And once it's there, it has a variety of different mechanisms by which it could be removed. It will diffuse in the air. It will diffuse, since this vadose zone is partly air and partly water, as well as quartz. It will diffuse within the air and the fluid, much faster in the air. Smelling scent in the room is much faster than that traveling in water. And it will also be carried down by infiltration of groundwater, by so-called advection. And so the two main things, and we can imagine all kinds of mechanisms by which it travels. Since the vapors are perhaps denser than air, then maybe not only does the plume try and move down by gravity, but the vapors will travel down by gravity. Once it contacts the groundwater surface, it can dissolve in the water and be carried as a dissolved plume, etc. And the groundwater flow is governed, of course, by the gradient of the water table, which defines the direction which it goes, and the permeability of that medium will define how quickly it goes. And so the mechanisms that we could imagine would be threefold. of which we'll really talk about just two. We'll talk about the left-hand two in some main detail, just because this is too detailed and too small scale for us. And that is by diffusion. So once it gets held in place by capillary forces, it can diffuse in the air within the porous medium. And also, once it's sitting there, it can be dissolved, not dislodged, and travel in the dissolved form to hit the water table, and then once it hits the water table, be transported by groundwater advection as a soluble plume. So those are the mechanisms we'll talk about. We'll deal with them in this order because that's the order of different complexity. I guess we won't talk about this one at all in terms of analysis. But I guess we have to be able to apply the same kind of rationale as we did for groundwater transport to the system. And so we need to know a couple of things. We need to know exactly how the gaseous concentration and the aqueous concentrations, I guess water in this particular case, are held together. And those are typically linked by Henry's law. And Henry's law connects the partial pressure of the vapor of the napple relative to the concentration that it would take up in water, its solubility in water, and it's linked by the so-called Henry's law coefficient. And so we can talk about that to be able to determine the interrelationship between aqueous and gaseous concentrations. And we will talk about that in a slightly different form. I won't dwell on it here. And we'll also use what we know about Raoult's law. And Raoult's law means that if we have a cocktail, the partial pressure or the vapor pressure of the component that's dissolved in the mixture is a function of its free phase vapor pressure, but multiplied by its molar concentration. So just as in dissolution in water, it's competing for solubility in water with the other components of the cocktail, and its presence in terms of solubility is just indexed by the molar ratio of the components in the solute. So that's we'll deal with those in due course, and we'll deal with it in slightly simpler form than those relationships. So if we're talking about diffusive transport, we've already talked about Fick's law. I guess this is Fick's first law, that the diffusive mass flux, that's a mass flux, is proportional to the concentration gradient of the gas, which is present within the pores, multiplied by a gaseous concentration gradient multiplied by the proportion of the pathway, which is the air-filled portion of the vadose zone, or the unsaturated zone. So theta G is the volumetric gaseous concentration. So it's a function of the total, so I guess phi G is equal to the volume of gas divided by the volume of the aquifer. These are volumes, so we know that. Because it only travels within the gaseous portion of the component. And so what we do is this, we put it into a continuity relationship, just as we did before, and we end up with a second order PDE that describes the diffusion in the system, second order partial with concentration in the gaseous form, an effective diffusion coefficient, and a retardation coefficient, exactly the same as our advection dispersion equation without the advection term. And so what we need to do, I guess, is figure out exactly what these equivalent components are. What is the magnitude of the retardation coefficient that affects this? And what is the effective diffusion coefficient of the vapor in the gas as it travels within the porous medium? And so we can think of the retardation coefficient in exactly the way that we did before. We could divide both sides through by retardation. And we also did it before with an advective term, right? We won't do that this time. but it certainly defines that the rate at which the diffusion can occur is reduced by the magnitude of this, which is bigger than 1 and less than infinity. But we don't know exactly what it is yet, but we could assume that that's the case. So the physical meaning of that is that if you look at the diffusion as a kind of Gaussian, spreading Gaussian distribution, we already defined exactly what this curve was. It was a complementary error function curve as a function of concentration and diffusion and time. Then the real meaning of what the retardation coefficient is it scales the length that it would travel according to the magnitude of this. So if retardation is 2, then it would travel roughly half as far as it would do at a given time because of the effect of the aquifer wanting to pull some of the component out of the gaseous phase and put it both in the water and in the solid, the water which is static. So that's the first of the terms that we need to define, which is retardation coefficient. The second one is the magnitude of the diffusion coefficient. And just like in water, or diffusing in a porous medium, we defined a term which we called omega, which was the tortuosity. Here we're calling it something different, but the same term. And it relates to the fact that in going from upstream to downstream, it's not going on a straight path, it's going on a longer traveled path than as the crow flies. And so we have to account for that in modifying the diffusion magnitude. And so before we said the magnitude of this might be between 0.01 and 1. Wasn't very definitive. I guess because we were always going to measure it in situ. Here, we could use something, you could use this in the aqueous zone as well. And this is just due to a relationship by Millington and Quirk from a long time ago, 60 years ago now, I guess, 62 years ago, which looks at the ratios of the total volumetric void volume relative to the part that's gas filled. So I guess this total volume here would be the porosity, right, if it's saturated. So phi T is equal to the volumetric moisture content of water plus the volumetric gaseous content, right? The sum of these add up to the total void content. And so if we apply this on a column from the ground surface down to the water table, then we can use the textbook or the reference book magnitude of gaseous diffusion coefficient for a chlorinated solvent, for TCE in this particular case, at 20 degrees centigrade, 8.1 times 10 to the minus 6 meters squared per second. And it compares with the aqueous diffusion coefficient, which is 3 orders of magnitude smaller, 10 to the minus 9, again, meters squared per second. And so if you apply this relationship to calculate the diffusion coefficient by multiplying through by the tortuosity, if you know what the gas content is in the upper portion, say, so this would be gas content of 25%, and if the total is 35, that means that the moisture content is equal to 10%. Right? That's consistent with this value here. Then if you use this relationship here and multiply it through by this diffusion coefficient, you get the effective one, which is 2.6 times 10 to the minus 6 meters squared a second. If the volumetric gas content goes down because the water content goes up, so this must be 30% now, right? Because of this. And then it changes so that the diffusion coefficient reduces by 2 orders of magnitude. And we can calculate that. And then when you go below the water table, I don't know why this is so slow on the Bluetooth now. If you go by the water table, of course, the appropriate diffusion coefficient wouldn't be diffusion in air at all because there is no air here, but it would be diffusion in the aqueous zone. So D star, which we used before, would be the equivalent one for diffusion in water, and presumably also modified for the tortuosity in the porous medium below the water table. So that gives us a way of being able to at least calculate the magnitude of what this term would be in defining this. So we've got an appropriate diffusion coefficient, so we could calculate how quickly this plume would spread and this red line would move towards the right in this particular case. So that's the first of those two parameters. So the second of the two parameters is figuring out exactly the form of the partitioning. And so you could imagine that before we had partitioning from water onto the solid, which could be carbon or it could be the solid. But in this case we have three potential phases. We have gas going into the water potentially, and then we have, once it's in the water, potentially partitioning on the solid. And the water in this case could be moving, but in the vadose zone it's probably more static than moving. And so we have to look at the effect of each of these to be able to figure out exactly what that is. And so one appropriate way to figure that out would be to evaluate exactly what the equilibrium concentration in the air-filled portions, the concentration of gas, is to the aqueous concentration. And we could define those by what I'll call a non-dimensional Henry's coefficient, because if these are both units of concentration, mass per unit volume, then the ratio of them has no units. And that's convenient for what we'll do. It turns out that the Henry's law coefficient, if you've seen it in other classes, is usually defined a bit differently. It's defined by the concentration in the aqueous form, which is the solubility, is the maximum concentration. And the concentration in gas form is just the vapor pressure of that particular solvent. And so these end up being not homogeneous in terms, they're both kinds of pseudo concentrations, but they're not homogeneous in terms of their units. And so this is one that you typically see in textbooks, and it's typically in units of atmospheres, meters cubed per mole. So a bizarre set of units as far as I'm concerned. So what we'll try and do is we'll try and reduce this Henry's law coefficient into the form that we see up above, this behavior, because it's much easier for us to use. And the second component is that, so this is defining how the gas goes into the liquid, how they're in equilibrium. How we look at the liquid going into the solid would be just by using the distribution coefficient as we did before. So we can define the distribution coefficient as the organic carbon partition coefficient, which we talked about determining last time. And if it's only going through the carbon, then we multiply by the fraction of organic carbon. And if we don't have much carbon in our system, then we have to use some other approach, but we can presumably get some value of Kd that we spent a lot of time talking about last time in 4.2. So with those two things, then we can make a stab at defining the retardation coefficient. And rather than derive it, I'll just quote exactly what it is, and it's this term here. And the idea is to look at the gas phase, and having the gas phase partition into the water. And since we know that the water, if it is a water-wet medium, is completely surrounding the grains, so the only way it can get into the grains is through the water. And so the typical way to think about this is going from the gaseous form into the water, and then going from the water into the solid as a sequence. And so if we do that, then we end up with a retardation coefficient, and a couple of parts of it are kind of familiar. So the one and this term perhaps are reasonably familiar, right? If we just looked at our aqueous retardation coefficient, it was equal to 1 plus bulk density divided by volumetric moisture content multiplied by Kd. And so these two parts here that I just outlined as one and this, all it changes by is this non-dimensional values of Henry's law coefficient. So this is saying that the equilibrium between the liquid and the solid is given by this, and this is that pathway, partitioning solid water to solid. And we have to add another part which represents the pathway from getting from the gas into the water, which is given by this. The volumetric moisture content, the volumetric gas content, and Henry's law coefficient. And so this represents the other term. And so that's the way that we'll use it. And so any transport within the vadose zone in the air phase will conform to this retardation coefficient. And so if we know what this magnitude is, the ramifications of it is that the plume will be slowed by that amount. If it's 2, it'd be slowed by a factor of 2. If it's 4, it's slowed by a factor of 4. And so we can use that to be able to get if we know the Henry's law coefficient, and we know what the organic carbon partition coefficient is from methods that we've used before, if we know what the moisture content and the gas content is, so I guess together these both sum to a porosity of 35%, just like the previous example. Bulk density is 1,650 kilograms per cubic meter. And then we can just look at what these individual components would be. And so if we look at scaling it with organic carbon, well, for this one, we probably shouldn't be using this relationship, right, from what we've talked about. We shouldn't be using Kd is equal to KOC fraction of organic carbon. We should only use this as the fraction of organic carbon is greater than, didn't we say 0.1% within the aquifer? So we probably shouldn't be using it for this. But I guess I'm not sure what the point of this table is, other than to say, obviously, the magnitude of the aqueous concentration or the retardation is hugely controlled by the distribution coefficient, which is controlled by the amount of carbon in the system. A lot of carbon, there's a huge retardation. Not very much carbon, there's none. Makes sense. And the part that is the partitioning from the gas to the water isn't affected whatsoever. And so this component might be a big part of what's going on if there's not much sorption onto the solid, or it might be a tiny part if there's a lot of sorption on the solid. And all we're doing is we're adding these together, I guess, and adding 1, right? So this value here is just equal to the sum of these 3 components. All right. So that means that if we're dealing with 2 systems, potentially, we're dealing with the aqueous retardation coefficient, which is the one I just added to that previous slide, and we're dealing with the gaseous one. And so these represent different modes of transport in different parts of our aquifer. And I suppose in the saturated part of the aquifer, this will dominate. And in the vadose zone, this will control behavior. And so what you could do is you could go through this thought exercise to be able to look at what the magnitudes of these retardation coefficients are in each of these portions of the subsurface, above the water table and below the water table. And I know it's kind of a horrible figure down here, but this is KOC. This is the distribution coefficient, KD. This is the retardation coefficient in the aqueous portion. So this is below water table. And this is above water table. And I guess all this does is to calculate from these and from the Henry's law coefficients for each of these 3 compounds, TCA, TCE, and methyl chloride, what the magnitudes of the retardation would be. And they come out to be 1.9, 14.2, and 16.9 in the below the water table. And they come out to be slightly different, as I guess this is the smallest one, 34, 55, and 73. And I guess the only point of note here is if you look at the order of these retardation coefficients, this is the smallest, this is the next smallest, and this is the 3rd smallest. So if you were monitoring at some location in the groundwater zone, I guess this is aqueous, right? In the groundwater zone, So this is aqueous, RA. Then the arrival time at this point would be in the order of the one with the smallest retardation first, right? So the arrival time would be methyl chloride, TCE, and TCA. If you look at the arrival times in the vadose zone, then this would be the first arrival, but then this would be the second arrival, and this would be the third arrival. So the arrival times of these two are actually switched merely on account of the fact that their retardation coefficients occur in a switched order. And this would tell you something about the timing of those arrival, but and of course the timings wouldn't be the same in the groundwater zone and the aqueous zone because the diffusion coefficients are different in both of those, right? We saw that in here it might be of the order of 10 to the minus 6 meters squared a second, and this might be 10 to the minus 9 meters squared a second. And so it would be much slower arriving here, but the relative orders of these would be in a different sequence that they arrived at that location. So that's a curiosity and would explain what you might see. The third case, I guess, is an exposition of that, and I suppose this is results from kind of a field test. It's kind of a field test because it's actually in a controlled environment. So it's in a sealed box, which is 3 meters tall by 10 meters wide. So 10 meters is about 30 feet. So probably a bit wider than this room, probably about the height of this room, and 10 meters in the other direction as well. And it's a fabricated experimental site where you can excavate the material, you can reconstitute an aquifer, and then within that reconstituted aquifer, you can put capillary tubes that are able to sample within the portion of it. It's in the vadose zone, so it's partially saturated, but there is no water table in here. And it's reconstituted, and then a source is put in here. I think it's actually pumped in as vapors. And the vapors are of methane, butane, and trichloroethylene. And these individual capillary tubes are just for sampling the concentration at a given time. All the figures on the left-hand side are the concentrations after a day. All the figures on the right-hand side are the concentrations after 3 days. And you see that for methane and butane, the plume has traveled the furthest, and for TCE, it's traveled least far. And so this is also some exposition of the impacts of the retardation factor in controlling the rates at which these components will diffuse, and the order in which they arrive is inversely proportional to the Henry's law coefficient, right? We know that the retardation is a function, is inversely proportional to 1 over the Henry's law coefficient. So as Henry law coefficient gets smaller, then the retardation gets larger, and therefore TCE is the one that has traveled less, because in this particular case, the Henry's law coefficient is actually the smallest of them. And these, by the way, are our, what we've called uppercase H, which is dimensionless. Right, I guess this is here, right? Both for the aqueous one and for the gaseous one. So the reason for that chromatographic separation, I guess it is, like using a filter paper dipped into dye, is that the Henry's law coefficients are different. So then the question is, how do we figure out exactly what this non-dimensional Henry's law coefficient is that we've quoted here and used if we only have the magnitude of the dimensional one? And so the easiest way to do that is to look at just manipulating exactly what the definition of Henry's law coefficient is. It's the ratio of the vapor pressure to the concentration in the aqueous form. These are usually, this can be defined as a mass per unit volume, but can also be defined as moles per unit volume. And vapor pressure is in a strange unit, which is it on here? It's not on here. Well, it doesn't matter. But we can get what this vapor pressure is. It's in units of pressure, I guess. And we can get that as a function of the ideal gas law. And the ideal gas law can be defined in terms of the density of the gas, the universal gas constant, the molar weight of the gas, and the temperature, absolute temperature. You've seen this before in your past, many of you. If you substitute the ideal gas law into this, you get this dimensional Henry's law coefficient as being defined as density, ideal gas coefficient temperature, divided by molar weight and concentration. If you separate out these terms here, as we have here, then you have the ratio of a density per unit volume divided by a molar weight, divided by a concentration. So these two represent a ratio of two concentrations. And so if you merely divide both sides through by RT, then this goes out to zero. Then these ratios of two concentrations are just equal to the dimensional form of Henry's law divided by RT. And so if we have this from a textbook or your reference book, and you have these other two terms, you can always calculate exactly what this is. And so a quick calculation using it for TCE here with appropriate units. Henry's law coefficient in atmospheres, meters cubed per mole. The units all drop out, as you can see here, and you end up with a Henry's law coefficient of roughly 0.4, which was the same as the one that we actually used up here. So that's where it came from. So you can always get, if you have access to Henry's law coefficient in dimensional form, you can always define it dimensionlessly. And if you can define it dimensionlessly, you can always be able to use it to be able to figure out exactly what this retardation magnitude would be. And that allows you to be able to say something about the motion of fluids. I won't go through that. I don't think I'll go through that. We've already said that. Raoult's law merely allows you to get the gaseous concentration as a function of vapor pressure and these coefficients. This is in terms of molar volume, and so if you know these other components, you can find out what the gaseous concentration should be for a cocktail that is a DNAPL that, like the Smithville DNAPL, contains a variety of different components. So how do we use these? Well, I guess we can use them in two forms. We said that we wanted to do two things. One was look at diffusion, so we've kind of done that. If we wanted to look at diffusion, we can solve this relationship of dc dt is equal to diffusion coefficient over retardation times d2c dx squared, where this is the gaseous concentration. And so all the equations that we had before, we should be able to use that. And if we know what this diffusion coefficient is and retardation is, then we should be able to figure out exactly what this Gaussian distribution looks like and evolves like. It won't have a front that moves from left to right because it's not advecting. It's just progressively spreading further and further over. So it would look like this. So this would be the 50% concentration at some later time, which would be this length here. So it would just spread like this. It wouldn't be a front that was moving. And so we should be able to figure out exactly what's going on there. It turns out that this kind of motion is the least effective and least rapid way of traveling. Of course, it might off-gas to the surface and volatilize off and be present in air monitoring. But the rate at which it can move is probably much faster and with much higher mass loadings if you look at being transported in aqueous form. So this is the other method that we look at. And of course, you can imagine that if it's being transported by water, a portion of the transport, this transport will be retarded according to the aqueous retardation coefficient. So let's see how we would solve that particular problem. pretty straightforward. So the idea is this. If we take, whoops. Yeah, okay. So you assume that you have something that's held by Capillary forces in the vadose zone. It's going to rain on the vadose zone, and some of it's going to get dissolved and going to be transported to the water table. How quickly will it move? Well, you know it'll move at the advective velocity of the water, which if the water isn't ponding on the surface and running off, so if everything that arrives on the surface infiltrates, then it will be the infiltration rate. Well, I guess by definition, the infiltration rate is the amount that goes into the subsurface, but divided by the volumetric moisture content. So this is assuming, this is assuming that in the subsurface, you'd have a whole bunch of grains, and around these grains, you'd have this saturation of water, which is pretty sparse. Most of it's air-filled, but you'd have a monolayer of water around every grain, and some of the pores would be infilled with water. And so this is the proportion of the total REV. So this would be the total volume of the REV is this square volume here. Volume of the REV. So this is the volume, total volume of the REV, which is water filled. So all this is saying that you expect that when water infiltrates on the surface, what it's going to do, it's going to travel in the only path it knows, and the only path it knows will be the connected pathway through the liquid in the subsurface, which will allow it to be delivered outside the REV. So this assumption here just says that all the rainfall infiltrates will transport only through the film of water which is present within the porous medium, and it's connected between the surface and wherever it goes downstream. So that's the velocity at which it will travel. If it dissolves stuff within this zone here and continues on its way, the rate at which it will travel will be given by the Darcy flux, which is this term here. Advective velocity multiplied by the water content is the same as taking the Darcy velocity and dividing it through by the volumetric moisture content, which is equal to the advective flux, right? So this is just a rearrangement of that. And the solubility or the concentration that's in the water. You've already done this. So this is the Darcy flux times the concentration. And this would be an amount that's moved per meter squared plan view. So you're looking a meter squared plan view of the aquifer, and this is the amount that's being washed down through that square meter. So it looked like this, I guess. One meter, and the flow is like this. And so that allows us to say what the mass loading is. So we might be interested to know how quickly this will dissolve, how quickly will it disappear, and what's the mass loading here that ultimately then is carried downstream as a groundwater plume. Is it small or is it significant? And so we're able to do that. I'm not going to talk about the advection dispersion equation because we'll do something slightly more simple. So what we can do is we can do that calculation for a particular field experiment. This is another field experiment that just happens to have been run at the Borden site, the one that we looked at for these clouds of chloride ion and TCE and carbon tet moving downrange for this aquifer injection test. But this is excavating out a hole, mixing TCE with some sand and refilling it in the hole and backfilling the hole with pristine sand, and then leaving it there and looking at what happens to the motion of that material from that zone into the water table. And of course also having sheet pile walls around this that actually penetrate into a a capillary barrier so that it's actually maintained within this, so not irresponsibly just watching stuff migrate. So it's actually contained within this cell, so to speak. So here, water content of 10%. I think don't see other terms on here. So it's at relatively low saturation. So it's at 16 liters per cubic meter. So a cubic meter is 1,000 liters. So I'm looking around for porosity here. Is it obvious? I see a moisture content. Do I see a porosity? I don't. So anyway, so if it's Borden, then the porosity is equal to 30%. So that would be if it was the pore volume is equal to, for a cubic meter, would be 300 liters. And this is less than the pore volume because it's smaller than that. I think it's like a tenth of or 15th of a cubic meter. So it's something like 160 liters, and so it's 16 liters, so it's something like 10% of the total volume is filled with TCE. So never mind, doesn't matter. So if you have 45 centimeters of infiltration, which is roughly the rainfall amount, you have this plug of material down here which is below the surface. It would be connected to the surface by water, so instantly it would be in contact with water. And so we can ask those two questions. How long will it take to reach the water table if it comes from here down to this? So you can imagine that if water is infiltrating at this rate at the surface, it's like a train. There's already water between that and the top of this component here. So as soon as the water comes in, the stuff at the top of the cell gets pushed into the cell, dissolves the components, and then carries them out. Likewise, the water that's been in the cell is already primed with solvent dissolved in it to be able to carry it down. So we can take the advective velocity, which is equal to the infiltration divided by the volumetric moisture content, which is equal to, actually I guess this is 0.1. And so this is assuming that if the water content is 0.1, does it have a gas content? No, doesn't define it. Then the advective velocity is equal to this. So it travels at 0.45 divided by 0.1, 4.5 meters per year. So if it has to travel 2.5 meters, this is about 6 months. So it travels 4.5 meters in a year. To go 2.5 meters, it's going to take half of that time, right? Just from the ratio. So that means it will travel like that. That is without retardation. So that's for R equals 1, goes to 2.5 years. But the retardation is really equal to 1 plus density over volumetric moisture content multiplied by KD. And I don't know what those terms are, but if we wanted to calculate that, then for R equal to actually, we probably have these data for Borden from our previous one. We certainly have them from carbon tetrachloride. Didn't we also have it for TCE? I thought we did. I thought actually retardation, is, if we use the Borden aquifer results, was something like 4.8. And if that's the case, then that means that if it's retarded by a factor of 5, then instead of being unretarded, then it would travel 5 times slower. So I guess this would be 12 years. Did I? Yeah. What's this? That's not right, is it? 2.5 meters a year equals 0.5 years. And so if it's a retardation of 5 rather than 1, then this would be 2.5 years. Right? So if we accounted for retardation, so obviously it's traveling only in the film, which is waterborne. It's free to be sucked into the solid, which is static, and so the retardation would be the aqueous one. We can also calculate what the loading would be. The mass loading would be the volumetric moisture content times the aqueous, the advective velocity. So this would be the Darcy velocity, these two, multiplied by solubility. And so if you have the solubility of TCE, which is 1100 parts per million, if it's a single cocktail, I don't think this was a single cocktail, but if it's a single cocktail, it would be equal to a mass loading of this, and it would be equal to about 0.5 kilogram per year. And the reason for getting that is that this turns out, if you multiply these together, you get 0.45 times this solubility. This 0.45 meters cubed per year is equal to a volume per meter squared. So this is the mass loading per meter squared, and so we have to account for that loading per square meter of the aquifer. So this would account to 0.5 kilogram per year per square meter underneath the cell, underneath the part of the cell that's been introduced into it, and that would give us the amount of loading. And so that would be what arrives on here. So what arrives here would be 0.5 kilogram per year. And I suppose really we should think about it not being a full 0.5 kilogram, because the appropriate area would just be the appropriate area which is directly under it. Because you can't assume it's the whole aquifer. You could assume that probably it would spread a little bit in going down there, but by how much, I'm not really sure. But taking this as being the tributary area immediately under this pod would be appropriate. And so you could compare that with a more sophisticated model that basically takes this pod that draws a center line through it and then creates a model that solves this. And so the model that would solve this would be one that would be meshed so that it would be like a slice of cake, so-called axisymmetric representation that would look like this. It would have this not canister, but this zone in here, which is the portion of the reservoir. And it would be a numerical model that would have a mesh going in it that would allow us to solve the PDEs for this behavior. So the mesh would just look like this. Takes a long time to draw. I think I've got a picture somewhere else, right? And all this does is allows you to be able to say, if you have this and you have rainfall washing down through this, what is the rate at which it would be dissolved from the bottom and then delivered to the aquifer? And what is the rate at which it would off-gas by vaporization outside, and maybe as a dense vapor also arrive at the water table? So this was aqueous, and this is dense vapor transport. So these are the kind of things that you need. I guess this is the 10% water moisture content, 25% gas content, fraction of organic carbon for Borden, super low, as we saw last time, less than 0.1%. Density of the aquifer, 5 meters depth, so this would be 5 meters here. And with these different coefficients, a gaseous gas diffusion coefficient, non-dimensional Henry's law coefficient, KOC, partial pressure of TCE, solubility of TCE that we used, and the geometry. So the geometry is kind of embodied in this, and it's an axisymmetric view, so it rotates, the center of rotation is around this center line that goes down through it. And if we're able to solve it, then the solution for this looks like this. These are two cases. And the two cases are looking at this behavior, where you have this zone which is put in place, and looking at it at six months. I guess the top one is 6 months, and the bottom one is a year. And these are just contours of how far the vapors of TCE have traveled as a function of time at that snapshot. So these are the concentrations. They're changing in concentration by an order of magnitude for each one. I guess the relative concentration is 1 at this point here, a tenth, a hundredth, a thousandth, a 10,000th. And I don't know what the difference is between the, right now, what the dotted lines are relative to the solid lines, don't know. So you see that after a year it's gone slightly further than after 6 months. And I guess more instructive is the fact that on the left-hand side, what's been put on the surface is an impermeable barrier so that the infiltration is stopped. So here the infiltration is shunted sidewards and can only get into the aquifer from this region here. And you see the concentrations. So the concentrations aren't significantly different in this, in traveling from left to right. This again is after 6 months and after a year with a cap on it. So no infiltration can occur in this particular case. Whoops. But what you see, I guess, this is the loading after 6 months. The cumulative loading after a year is almost 16 kilograms dissolved out of here. And if you look at this particular case, the amounts are much less. So this is a factor of, this is less than a tenth, right? This is probably a 15th of this amount, and this is roughly 20%. Yeah, about 20%. And so one obvious way to be able to stop this is that clearly transport advection by groundwater, by infiltrating groundwater, is a huge loading to the subsurface. And an easy way to avoid that is just to transit the water off it so it never sees it. And I think that's all we'll do. So that's the final story. So we looked at 2 of the 3 scenarios we could look at, and we didn't look at the last one. I guess this would also, actually this model that we looked at would also include this last scenario, which isn't a big effect. And that is that in addition to just diffusion without infiltration, you don't get very much loading on the water table, and it can off-gas. If you have diffusion but with infiltration and advection onto the surface, you get a lot of loading into the saturated groundwater zone that then can be carried downstream as an aqueous plume, but can also be diffused in the subsurface as a gaseous plume. And the other thing that we didn't look at is the effect of the gas coming out of here, being denser than air, and contacting the top of the groundwater zone merely by sinking, as vapor would do in a room. Like if you put dense vapor in a room, it sinks to the floor. And this is all that is. And once it sinks to the floor, which is the water table, then it can diffuse into this at a low rate. But this component is not very much. So that is it. That's it. So I guess, can I go back to the top? Can I go? So that's what we'll do before spring break. And so if you go back to, I guess it's elsewhere. If you go back to our syllabus, if I have our syllabus, which is this, I guess that's something else. Do I have a syllabus just on its own? Is that we are exactly here. So what we've covered is everything in the vadose zone in terms of free phase transport. Motion is constrained by interfacial forces. Ability to understand that behavior in terms of capillary pressure versus saturation curves and relative permeability magnitudes. Getting into the groundwater saturated zone, transport by advection and dispersion, understanding controls of that by sorption and retardation, what that means in terms of rates of transport, and we've now just applied that to understand how behavior occurs in the vadose zone, which follows on directly for that. So the only thing left for us to do would be to talk a little bit about models that allow us to do that, kind of like the piece of pie that we just drew up to solve the vadose zone transport model. We'll talk about very simple models on the Tuesday after spring break, for which I won't be here, and so it'll be online. And then we'll spend 3 periods talking about, now that you know what the processes are, now that you know what the properties are that control those processes, porosity, permeability, sorption, the depth of the thicknesses of zones of different media, the depth to the water table, the concentration of water within the vadose zone and below the water table. We'll talk about how you go about getting that information to be able to put it in the nice, neat little assignments that we've had, where we've always assumed that we know the stratigraphy, we know the concentration distribution, and we know what the properties are of the subsurface. And so the method to do that is to drill some holes, to do some sampling, to put in some instruments like piezometers, and perhaps to use pump testing and aquifer testing. We've talked about already some of those in part 3, and also to talk about using geophysics to pick this out as well. And that's what we will complete talking about 2 weeks after spring break, and then you'll be on your own for your remediation presentations.